All right. Good morning. So I want to start talking about Boltzmann transport, and I want to show you, at least at the moment, classical diffusion. So when we introduced like semi-classical equations of motions, we saw that there were like some K and R. They were like simultaneously defined, and they were like classical phase space variables, and they had like some equation of motion that was actually coming from quantum mechanics. That's why we said like semi-classics. But now we want to like go beyond. Question? No. We want to go beyond that, and we want to talk about like occupation probabilities, f of r, k, and t. So we introduced like a probability function. This is like a probability. You have like an electron at r, k, and t. And once, okay, at the moment what this is, we don't know, but once you have this object, you can calculate all observables. For example, you can calculate density by summing over all possible k vectors, d cube k over 2 pi cube f of r, k, and t. In the case of spin system, sometimes people put 2 here, but let's not worry about spin at the moment. It is not relevant to present discussion. And we can also calculate, for example, current. And in that case, it's going to be exactly the same thing. If you are calculating charge current, you need to multiply with charge. If it's particle current, just drop this, and it's going to be velocity, which will depend on k, and possibly also band index, and we are considering only a single band at the moment. You can calculate, for example, heat current, exactly the same thing, and typically we show heat current with E because it's like some kind of energy current, and for that I'm going to write it like E n of k minus mu, and here mu is the chemical potential. Again, all of them should have like a factor of 2 if you are studying spin a half system. And here v is, again, this is 1 over h bar del E n of k and del k, which is actually a quantum object that came from the solution of Schrödinger equation. And the next thing is how do we obtain this f? And f, we need to derive like equation of motion. So f is a function of r, k, and t. Typically people introduce like a phase space, and they account what's coming inside the phase space and what's coming out of the phase space. But I think the derivation is very easy. So we want to obtain total time derivative of this object, and it should be equal to just chain rule, right? It is like there could be like some explicit time dependence plus, now there's like a r dependence, so I'm going to do dr dt dotted del f del r, plus there can be a k dependence del k del t dotted del f del k, and this should be equal to 0. Yes, actually let's do the general case, and this should be equal to what we call del f. This is like a notation, I'll explain what this is. Del f del t collision. Like there's like some phase space, so this is r and k, there's something coming in, something coming out, and net change should be given by this, and subtracted the collision integral. So here, this is exactly like in the semi-classics, V, and we are going to substitute V of k for this, which is going to be 1 over h bar del E del k. And here, this is h bar times this is force. This is force divided by h bar, and by Newton's equation, it is going to be minus E over h bar E cross B. So what this says is like all bend effects are taken into account here, right? I solved the Schrödinger equation, I obtained epsilon, and then I turn on slowly varying weak external E and B fields. All of those are taken care here. And anything else, like if I can have like impurities, phonons, electron-electron interactions. Oh yes, it is E. Thank you. So this is E plus V over C cross B. Thank you. And everything else is taken care here. And today I'm going to just consider impurities, and I want to obtain diffusion equation from this transport equation. So this equation is called Boltzmann transport equation, and this thing is called collision integral. So let's only consider impurity, or sometimes people call this disorder potential. And like there is like an ordered crystal, and on top of this ordered crystal, maybe I have defects, maybe I have like some implantations, maybe I have some dislocations. Whatever they are, we don't care. But they are like impurities of like periodic crystal structure, and they are going to prevent perfect Bloch waves, and the Bloch waves are going to scatter due to presence of impurities. And we can write the collision integral carefully and find what's coming in, what's coming out, but I think we don't need that much, and we can do something called relaxation time approximation. And I think once you see what it is, I think it makes sense. So in that case, so del F del T collision is going to be so there is like some equilibrium. Suppose you have like some equilibrium F K of naught, and you go to non-equilibrium from this F naught. So you create some non-equilibrium, let me call it like Fk minus Fk of naught. And because these equilibrium deformations are going to be slow and they are going to relax very rapidly, we put like a time decay to these modes.
What is F0?
I'll introduce F0. So at the moment we don't know. So this is equilibrium distribution, but we are going to take it to be Fermi-Dirac. Fermi-Dirac distribution. Actually, let me write that. I think it's a good point to. So this is going to be 1 over e to the beta epsilon of k minus mu plus 1, and mu is chemical potential. Good, then our equation is del F del T plus V dot so this is F. There could be like some explicit time dependence, that's why this is written here. Del F del R acting on F plus del actually let me write it like force. Maybe this is, did I get wrong? Yeah, this is V. I'm using V, so it is V. So this is going to be F over H bar, del over del K dotted onto F, and this is equal to minus 1 over tau F minus F0. And all these F's are K and possibly R dependent. So we can solve pretty much any kind of problem with this. We can have like electric gradient. We can, so if there's like an electric field, you can put it here. If there's like a thermal inhomogeneity, you can put it here, right? There's del F, del R. There can be both. You can put like an explicit time dependence here. And like I said, at the moment we are interested in impurity scattering, but if you have other things, they are also going to have this form. And different scattering processes are going to be added here in a linear fashion. What is called so-called Mathiasen rule. But I think we don't need any of this. I just want to derive diffusion from this. I assume steady state.
First two terms are 0?
Yes, so steady state, not the first two terms, and no external force. But typically people do what you call it. They drop this and they put electric field, and from the electric field you can calculate, for example, the root conductivity. And Gervin-Young has that, but I don't want to do that. I want to go for diffusion. So let's consider 1D, and I want to put like some density in homogeneity, right? So this is N, and I want to see how this N is going to evolve in time due to this Boltzmann equation. Then F is 0, del F, del T is 0. And since it is 1D, I'm just going to take one-dimensional form. So this is V, let's take Vx, and this is going to be del x is equal to, I think I'll leave the arguments implicit. So this is minus 1 over tau F minus F0. Now I can write F in terms of F0, so this is minus tau, and tau is gone, and this is F0, and this is gone, and this entire thing, okay, let me push it to the center, so this entire thing is F, and I can erase this. But here there is like this equilibrium density that's determining F, but F itself is also determining F, right? So this is like an iterative equation. You need to substitute something for F, find F, and then substitute F again, and then so on. And so for density in homogeneity, we need to calculate this del F, del X. So del F, del X is equal to, so let me consider this equilibrium, so this equilibrium form is 1 over e to the u plus 1, and u is, I define like a short variable, beta epsilon minus mu. So to take the derivative, I'm going to take derivative with respect to u, minus 1 over e to the u plus 1 squared e to the u, and del u del x, but only mu, okay, only mu is x dependent. Mu is, that's what the density in homogeneity means. Then I'm going to push, this is beta, and this is minus del mu del x. Is that clear? I just did the chain rule. But I can look at this, and I can also take derivative with respect to epsilon. Why? Because this is like a Fermi function. And so this is f, this is epsilon, there is some mu, and especially at low temperatures, this Fermi function is going to be very sharp, something like that, right? And its derivative is going to be like a Dirac delta function. And we like Dirac delta functions because it prevents us from having to take integrals.
Why take derivative of Fermi distribution?
Because in the equation I have del f del x, right? Here I need to take del f del x, but I have to take derivative with respect to x, but there is no explicit x. The x dependence comes from mu, and mu is inside the function.
But it's f, not epsilon.
Yes, exactly. So that's in the like small deformation limit. I say that f is deformed in such a way that I just need to deform mu to lowest order in this equation. Now del f del epsilon. Yeah, that's a good point. Yeah, that's how we calculate things, and let's see what gives us. So del f del e is exactly the same thing, minus 1 over e to the u plus 1 squared e to the u beta times 1, right, because epsilon. And from here I see that this piece is exactly minus, with this minus, let me put minus later, this is del f del epsilon. Then del f del x is equal to minus del f del epsilon times del mu del x. Did I get that right? Yes, good. Now we are trying to see the current. Let's calculate the current in x direction, and I'm interested at the moment in particle current, and this is d cube k over 2 pi cube. This is f of k, and if you want r, and for particle current I only put v, and I'm interested in diffusion in x direction, or like current in the x direction. If you need like a charge current, just multiply this with e, right? Minus e, then you have the charge current. And inside this, I'm going to substitute this f, if you want the zeroth order, which is Fermi function, plus f first order. And the first order is going to be, okay, so this is zeroth order, this entire thing is first order. And I can, by iterating this, I can get second order, third order, higher order terms, as many terms as I need. But when I look at this equation, so this is the equilibrium distribution function, and in the equilibrium, by definition, I don't expect to see any diffusion. Of course, if I didn't know that and I substituted this in this equation, from the symmetry of this f function, I would immediately say this is 0. But on physical grounds, we can also cross it out. Then this thing is going to be equal to, I'm just substituting that, okay, so this is del f. I need to substitute this entire thing. Let me take that. So this is here. I need to sum over all k. So this is f, and I need to, this is v. And there's vx. Let me put this square and erase this one. And I like writing this tau in front. Minus tau. Okay, that's it. And now we have to take this integral. And to take this, okay, this del f del x, we calculate del f del x. Let me also write this one. So this is minus del f. Okay, this entire del f. Okay, let me do it in 2 lines so that we can compare what is happening. So this one, and I want to substitute this del f del x, this piece. Good. And I want to consider like small density in homogeneities, and what this means is like higher order derivatives are going to be like 0, and also the first order derivative is all going to be constant because we are looking at the linear order anyways. So what I'm going to do is I'm going to take this out, and I'm going to say this is like a constant independent of integral, and we have an integral that's in terms of v and f only.
Isn't it constant? Del f over del epsilon.
Del f over del epsilon is going to be delta epsilon minus mu in a little bit, right? Because f is a Fermi function, just like we said. And if, okay, this is f, this is epsilon, and this is epsilon is equal to mu. And the derivative of this with the proper minus sign is going to be this peak, right? It is like a delta function, if you like. That's the whole point of doing this derivative in that way. Now I want to take this integral. So this phase space, I want to spend just a few minutes to show you the details, which is important in technical calculations, which is simple, but sometimes I see people having like a hard time. So this is d cube k over 2 pi cube is going to be equal to 1 over 2 pi cube. So this is k squared dk, and this is d phi, and this is d cosine theta. So this is going from 0 to 2 pi, this is going from minus 1 to 1, right? This is the three-dimensional integral. I just write cosine theta and phi. This is azimuthal angle, this is polar angle, and this is the radial variable. We are in k-space spherical coordinates. And for that, what I want to do is, okay, and what do I have is epsilon is h bar squared k squared over 2m star. Everything about band is taken care here inside the m star, right? I can just approximate any band with like parabolic dispersion. Then so what I want to do here is, let me not clutter it. So I want to do this. So I want to put the epsilon here and multiply with the epsilon. And here I want to write this 1 over the epsilon dk, right? And so this is epsilon, so this is the d epsilon dk is going to be equal to h bar squared k over m. Let me not write m star over and over again, so we know it is band mass anyways. So this is h bar squared over m k, and here from this equation k of epsilon is equal to root 2m epsilon divided by h bar squared. So this is so this k is going to cancel this, and what remains is like some epsilon dependent object. So I want to push 2 pi here, so this is going to be square, and I want to push 1 factor of 2 here, so this is going to be 4 pi squared, but since I pushed 2 here, it's going to be 2. Right? And here, hopefully all of you have calculated density of states in 409, right? And what remains here is this entire thing. You can see like there are like 2m, h bars, blah, blah. They all add up to give you density of states. And I think I used d or rho for density of states. Oh, okay, I used rho here. Rho, so this is density of states, which is del n del e, right? And here what remains is exactly the same thing. Let me just copy. Good. Now I'll substitute this integral here, and I'll just take the integral. So we are, if you remember, trying to calculate jx is equal to so this guy and so this guy. So this one I'm going to push a little bit.
Isn't it just one?
Which one is one? I'm trying to take it right now. The epsilon dependent part is here. This is delta epsilon minus mu, and here I have Vx squared, and Vx squared I'm going to substitute V Fermi squared times cosine squared theta. Good. We are almost done. So this is minus tau del mu del x. So this is mu at Fermi level, density of states at the Fermi level, and this integral is easy, right? This is 1, but this one is going to be 1 over 2 V Fermi squared. So this is 1 over 3 cosine is x squared. So this is 1 minus 1, and this one is going to cancel this two, and this is going to be 1 over 3 V Fermi squared. Minus tau delta x of mu 1/3 V Fermi. Okay, good. Now here, looking at this, I have like this 1/3 V Fermi squared tau. I want to introduce so-called diffusion constant. Diffusion constant, which is shown with D, is equal to 1/3 V Fermi squared tau. So this is an important thing to know. There are other ways to derive this, but now in the present context it came from the diffusion equation. And so this is one-dimensional gradient. We can generalize it to 3D, and in 3D it's going to be J is equal to minus D rho of mu gradient of chemical potential. But the density of states is defined by dn d mu. But how many? Dn d mu. How many states I have at a given level? So this is going to be minus d dn d mu, and this is gradient of mu. And from here you can see mu and mu. This is like a chain rule here. So this is minus d gradient of density of R, if you want. And this is what we call Fick's law. You could derive this without knowing anything. You didn't need Boltzmann equation or anything. But I just wanted to show you a use of Boltzmann equation, and there are other things that we don't need.
How do you change rho mu to dn over d?
So this is the definition, right? I think you are probably more familiar with like this dn de, right? This is the density of states. But first we are looking at the density of states per volume. So n becomes n, and we are looking at the Fermi level. So epsilon becomes mu. It says the density of states at the Fermi level. Now we can calculate electric conduction, which is just this quantity multiplied with E. So let me just use J of E for that, is equal to E times D del N del mu times gradient of mu. And in the case of electric potential, mu is the chemical potential, I'm going to just take it minus E times phi, or if you want voltage, V, and gradient of mu is I'm going to take minus E gradient of V, but this is minus E, right? Gradient of V is minus E, so this is going to be E times E. Then this equation is going to give me E d del n del mu times E times E, and I'll combine these two E's. And in this expression, anything that multiplies E is going to be conductivity, sigma. From here we obtain sigma is equal to E square d del n del mu. So this is also very important, and this is called Einstein equation. This also can be derived almost at high school level, right? Without knowing anything. I didn't do it, but maybe I can give you as an exercise. If you can do it, look at the textbook exercise. Just consider isolated system. And inside the isolated system, you put like a gradient, so it's something like that. So there are like some hard walls, like a particle in a box, and inside this box you write some minus E times phi. You put like some electric potential if you want, and there's like some chemical potential. So Gervin-Young shows mu tilde for this, and your chemical potential is the distance to here. So this is mu, so mu tilde is equal to mu minus E times phi. And now what you need to do is there are like two kinds of currents. One is the current due to this potential difference, and this potential difference is going to generate a density in homogeneity, and then that density in homogeneity is going to generate a diffusive gradient. And in the equilibrium, because this is isolated system, you balance these two, and then you need to obtain exactly this thing. So you don't need Boltzmann, or you don't need anything else. So consider this and obtain Einstein relation. So I want to spend just a few minutes to discuss this, because this is like kind of like an important relation. So this simple, and it looks innocent, but it has a lot of physics actually. And by just looking at so this expression is correct, right? So for example, this argument is correct whether you have electron-electron interaction, whether you have whatever, you can put everything. So this relation is generic, and we can consider it to be a general result. And we want to understand when do we have insulators and when do we have metals. So insulators versus metals. And since E is electron charge, I cannot take it to be zero, right? Either D can be zero or del mu del N can be zero. And these are two different kinds of insulators. So case 1, del N del mu can be zero. So what this means is this is zero density of states at Fermi level mu. So there is like, that means there are no states at mu. What does it mean? If there are no states at a given energy, it is insulator, but what kind of insulator? What's that? Gap, exactly. It is the, we are in the gap, so there is like some energy. And if you put chemical potential right here, so this is mu, because there is no energy, there is no level here. If there is no level, density of states is 0. If density of states is 0, sigma is 0. So this is what we call band insulator. So this is case 1 of this. But there is another del mu. There is another case for this del mu del n del mu. Even if your Fermi level is inside band, if you have electron-electron interactions, you can gap out. Right? This is what we call like mode insulator. Even if you are not in like a single particle band gap, you are in like in the middle of a band. In the non-interacting picture, it looks like it should be a metal, but because of electron-electron interactions, it gaps out, and del n del mu is going to be 0 due to electron-electron interactions. And we call these mode insulators. We won't talk about this at all for this course. It's a little bit advanced stuff. And the case 2, okay, this is del n del mu can be 0 in maybe other ways. This is just 2 possibilities. And the second one is d can be 0. 2, d can be 0. Then sigma is going to be 0. So in this case, you have like electron states, right? This is finite. Even if you have finite density of states, you have electrons at the at the Fermi level, and no electron-electron interactions, no electron-electron interactions. You can get d is equal to 0 due to what we call interference. So this is purely quantum effect, quantum interference. So in the Boltzmann equation, if you noticed, this is a semi-classical equation, right? And even in the collision integral, there is no interference whatsoever. Like these are not waves; these are classical waves that the classical probabilities that propagate without any possibility of interference. But in real material, if we have quantum mechanics, we have waves, and waves can interfere, and this interference can localize electrons by setting d is equal to 0. Maybe I can give you a cartoon of this, which we are going to talk a little bit later. So I can go from, for example, electron can go from here to here to here and come back. So this is like that. Or it can reverse it can go like this, or it can go the other way. It can go like this, like this, like this, and like this. And these two paths, right, they are exactly the same thing, reversed in the opposite ways. They are going to interfere destructively, and that means they cannot diffuse away from the starting. If this is the starting point origin, they cannot diffuse away from starting point. And in this case, d is going to be 0, and what we call this is like Anderson insulator. So we have band insulators, we have mode insulators, and we have Anderson insulators. And the thing we are going to discuss in Anderson insulator is like for weak disorder, right? If weak disorder, so this cannot happen, or even if this happens, it happens very rarely, because, right? Electron just propagates, it cannot find any impurities to scatter and turn back. Then it is going to be a metal. And if you get to strong disorder, there will be a point you cross from weak to strong, and there will be a so-called metal insulator transition, and we are going to call it Anderson localization. Okay, I think that's it for today. Any questions? So this was like classical diffusion. Next time I'll try to put a little bit quantum to this. Maybe I'll first introduce diffusion a little bit more, and then we are going to make diffusion semi-classical.